So I'm going to talk about some distributed memory programming models, and I'll start by talking a little bit about some of the big machines around, because I'm going to tell you about basically the most popular parallel programming model these days for any kind of large-scale parallelism, which is the message passing model or interface MPI. And then I'll tell you one about another language that I've been working on for a number of years, which I think is going to soon take over the world, but we'll talk about that later. So the top 500 list, how many people have heard of the top 500 list? Did Jim already mention it? I think he probably did. Okay, so you know this is the LINPACK benchmark, and it's solving a problem that's dominated by matrix multiply. So it's usually about the fastest thing you can get to run on one of these big machines. Interestingly, so I'm also the director at the NERSC facility. So how many of you have logged into NERSC? Okay, good. So I'll say a little bit more about that, and we can answer any questions about it if you want in a minute. But what I learned about the LINPACK benchmark in running a facility is that the LINPACK benchmark is no longer a performance benchmark, it's a reliability benchmark. Because the question is, can you keep your machine up long enough for it to actually finish solving AX equal B for the largest problem that you can fit on that machine? You always want to have one of the largest problems on the machine because it gets better performance. So anyway, it's still a sort of interesting benchmark, although not necessarily for the reasons that people originally thought it would be. In terms of the history of the top 500 lists and of these machines, it's just, I think the most useful thing actually about the top 500 list is the historical perspective it gives. We can argue about what kind of insight, if any, we get from the actual number of any particular machine, but it's really useful to see the historical trends here. And the blue line there is this is the fastest machine. You see it's a fairly, on the top 500 list, it's a fairly bumpy curve. These two smoother curves are the sum of the top 500 machines on the list, and there's the bottom of the top 500 list. So it's always interesting to see how fast the slowest machine on the top 500 list, because that gives you an idea of kind of how fast you that one of these high-performance computers is. Most of these high-performance computers are within that top 500 range someplace. So you heard already, I think you probably even saw this slide about NERSC, so I won't say a lot more about it. But I will stop on this slide, which Jim, I think, did show you. I think most of your assignments are being done on Hopper, which is a Cray XE6 system. And if you want to, you have access to both the Dirac system, which is a GPU cluster testbed. We call it a testbed because we don't promise that it's up all the time or that it's supported quite as well as the other machines. It's not a production machine. And for the most part, people are testing it out. It's relatively small in terms of the number of nodes, but you can try that out if you want to try out parallel GPU code with, say, message passing MPI and CUDA on the nodes. So those are NVIDIA GPUs. But the main system that I think you're using for the assignments would be either Hopper or the Franklin system. Carver is also a very popular kind of standard-looking Linux cluster. So any questions from people who've logged in, have questions about what these machines are or anything like that? Okay. So Hopper right now is the number 8 machine on the top 500 list. It's right there. It's just over a petaflop of peak performance, of LINPACK performance, and a little bit higher than that, about 1.3 petaflops in terms of its theoretical peak. That is, if you add up the peak performance of all the processors in the system. So this is the latest of the top 500 list. So it started actually out at number 4, and it's been sliding down. It will slide down slowly every 6 months as other people install new machines. So, as I said, the most interesting thing about the list is looking at the trends, and this shows the architectural trends over time, which have really have changed substantially. And the MPPs, those are kind of customized massively parallel multiprocessor systems, parallel processor systems, clusters, which are predominantly what we see on the top 500 list today. And so those would be more like Linux clusters and things like that. But you see that you don't have to go back very far, back in the 1990s, and the top 500 list had a lot more of these shared memory multiprocessors on it. And if you actually follow it back further, you'll see vector supercomputers as being much more dominant. So these are the vector supercomputers here, the single processor machines. So those are the vectors. So I think this is probably, as I said, one of the most interesting things to look at in the list. So the question then is, over time, how has our programming of these machines changed? Because the architectures have changed dramatically over time. So People like to refer to this as the Ecosystem for High Performance Computing, or HPC. There was a report written, almost 10 years ago now, on the future of supercomputing that looked at all the different parts of what they called the ecosystem, which is that it's not just about what kind of computer systems you have, but also what applications are you running, what kinds of software are you running on these systems. And there was sort of a stable ecosystem in the late 1980s. This came from the Cold War and lots of big oil money being spent on supercomputing, high-performance computing. So what we had was, those were the spending numbers, and what we ended up with were these powerful vector supercomputers, which we now often refer to as the dinosaurs. So were these vector supercomputers, and how were they programmed? Well, they were basically programmed with Fortran. Not quite pure Fortran if you're a language purist. They actually did have annotations in the language for vectorization. So you couldn't just take your Fortran code out of the box and run it at any kind of reasonable performance on these vector machines. It would run, but it wouldn't run very well until you spent some time figuring out how to annotate that code with things like IVDEP, which says this loop really is a vectorizable loop. I don't care whether the compiler can figure that out or not. So that was a kind of a stable ecosystem, and these were actually very popular machines because people had a lot of Fortran code and they could fairly easily adapt them to those kinds of systems. Now, along came the commercial off-the-shelf technology, which was so cheap by comparison to these more custom-made vector supercomputers that they really took over the high-performance computing area, and we had these Beowulf clusters, as they were called. So there's the Beowulf clusters coming in, and this is what the ecosystem looked like in sort of a stable form in about 2006. And the way in which these were programmed, whether it was Fortran or C or C++, it was programmed with this library MPI that I'm going to talk about. So there's now a big investment in these MPI applications, which is why people don't want to change to anything else. But they have changed once before. They changed from these vectorizable Fortran code into something much, much harder to program in, namely into message passing, or MPI. And now the question is, what are we going to do next? So if you look at the NERSC system roadmap, the two main systems we have on the floor right now are Franklin. We did an upgrade of Franklin from a dual-core system to a quad-core system. That's kind of following all the trends you've heard about multi-core. Then we installed the Hopper system, and we're still running these two systems at the same time. We're looking at we'd like to have about a 10 petaflop system. We probably won't hit 10 petaflops because we're limited by power in the facility right now. We're building a new building, and once we build that new building, we'll be able to put in these larger systems over there. But now what we're pretty sure about is, and that, by the way, is an exaflop out there, sort of petaflop, which is 10 to the 15th floating point operations per second. So we're looking at the next major milestone is an exaflop with 10 to the 18th floating point operations per second. So how do you program these things? Well, Franklin was 90% of the programs written on Franklin are written with MPI, just flat MPI. The language they used with MPI varied across the applications. There's still quite a bit of Fortran within the NERSC workload, but there are other languages like C and C++. There's also things like Python that get used on the top of these applications, but we call that flat MPI because it wasn't mixed together with anything else. Now, as we move towards Hopper, we are encouraging our users to take advantage of the fact that this Franklin system had 4 cores per node in it, so 4 cores in a shared memory space. So you weren't really wasting much shared memory hardware if you ran an MPI process, which is sending messages between those cores on that kind of a quad-core platform. Hopper, however, has 24 cores in a node. It has dual sockets, so there's 2 sockets that have shared memory between them. And then within those sockets, there's 2 6-core dies that are on the same chip, and so there's 24 cores in a node. And the real issue is that the amount of memory per core has not gone up in these two systems, and so we're really looking at trying to get people to use the shared memory on the system rather than doing message passing between them. Now, as we look forward, then the big question is, what are we going to do next? Are we going to be building as the Chinese supercomputer that's on the top of that list? Both of them are actually GPU-based systems, as is one of the Japanese systems. Those 3 systems that are on the top 5 spots in the top 500 list, including not including the very first one, are all GPU-based systems. So the one that's not is the Japanese system, and the Jaguar system, which is also a Cray very similar to the Franklin system, actually, that's at Oak Ridge. And then the Japanese system is actually built out of really lightweight cores that is more like a blue gene system, if you're familiar with that, but does not have GPUs. But as we look forward, we're seeing trends in heterogeneity, and heterogeneous processors such as graphics processing units being used in the systems. And the question is, what are we going to program in? MPI plus X seems to be the most popular answer. And what we're trying to do is to avoid having people learn one programming model, rewrite their codes in MPI plus CUDA, for example, and then rewrite them again into MPI plus X. So this is one of our challenges as we look at the programming models going forward. But the reason we have the testbed DRAC on the floor is so that people can try CUDA and mixed CUDA with MPI, that kind of a programming model. Okay, so down to something a little more practical. If you're not familiar, how many people are actually already familiar with MPI? Okay, so there are a few, not too many. Okay, so MPI stands for Message Passing Interface, and it's a library. And one of the advantages of having a library is that you can glue MPI onto a lot of other languages. In particular, here you can use it with C, you can use it with Fortran 77 or Fortran 90, or even latest Fortran versions. You can actually use it with C++ and other languages. You can use it with Python and things like that. You do have to have an interface for Python to use it with each of those languages, of course. But it is a library, and we're going to start with a really simple program, which is just going to create 4 processes and write out the processor numbers of each of the processes that's in the system. And by the way, I will often go back and forth in this lecture between processes and processors. Typically in an MPI application and even in a UPC application, when I talk about UPC at the end, you run a process per core, although as I said before, you don't necessarily have to do that. But for that reason, I often think of each process as a processor. So a couple of important questions that come up as soon as you're trying to write an MPI application is, how many processes are there that are participating in the computation, and which one am I? So these are things you kind of need to ask about in order to get the code, to write the code in a way that makes it portable. You don't want to write applications that are hard-coded for 16 processes or 10,000 processes or whatever. You want a program that's going to be able to adapt to whatever processes you decide to run it on, and so you will write it in such a way that it asks for the number of processes within the program and then programs to that number. So the two important variables that you can read in an MPI application to get these two numbers are com size, which is the number of processes, and then com rank, which is the processor number, which is between 0 and the size minus 1. That is the number of processors in the system. So here's the the simplest MPI program written in C. I apologize to those of you who are Fortran programmers by nature. I'm more of a C programmer, although really probably more of a Java programmer than anything. But anyway, this is what the C program looks like. And there is online, if you look at the online lecture notes, you can see the versions that are in Fortran and C++. So this is kind of usual C junk. For those of you who aren't familiar with it, it's just getting in some arguments and so on. But here's the MPI calls. We first of all have to initialize MPI. It's a library. It's not set up by default in the application when it starts to run. And then you can ask for the rank, the total number of processes in it, which is going to be written into this. This is kind of weird C syntax that says write it into the variable name ranked, because you're passing in a pointer to rank, and you're doing the same thing with the, sorry, that's my rank within the set, and then the total number of processes in the system, and then you can print those things out. At the end, a good MPI program will finalize, which means it cleans up after itself, and then you just return from that. Any questions? Okay. So a few notes on that. As I said, they have to start and end with init, and they should end with finalize. Com world is one of the things that's built in. There are more sophisticated kind of communicators that you can ask for subsets of the processors with, but for your first set of MPI applications, you will normally just want to use com world until you get a little bit more familiar with the language. And so it's one of the standard, what's called a standard communicator. And the reason that it doesn't just automatically know how many processes are, you have to ask about the world communicator, is because of this property in MPI that you can also run MPI programs on subsets of the processors or functions on subsets of the processors. So each of the statements executes independently in every process. So the way to think about it is that main function gets replicated on every processor, and each one of them runs a copy of that main function. At least that's just intuitively the way to think about it. But they're not in lockstep. Okay, so one of them, for whatever reason, one processor might be running slower than another one because, say, there's stuff polluting its cache, and so the program is just not running at the same speed. And so they can hit the same statements in the program, even if they execute the same sequence of statements, they can hit them at very different times. So MPI, I'll say, I/O is not in the original MPI 1 specification. By the way, the standards committee for MPI is working on MPI 3 right now, but it is, so I/O is actually part of MPI 2. And the thing that you need to know is actually how to run a program, and this is, by the way, where you specify how many processors you want to use, and also how many processes you want to use is in this job script that the MPI run command that runs after you've compiled the program. Okay, so trivial MPI program so far. If we want to do send and receive, the idea is you've got two different processes, and they're going to send data from one to the other. They can't see any of the variables that the other process has without them. They all have a copy of any of the global variables in there in the program. So now if you want to send data, you have to figure out how you're going to describe the data, how you're going to identify the other processor that you're going to send the data to, how does the receiver figure out at which message it should receive at any given point in time, how does it screen for the messages, and what does it mean for the operations to be complete, which is probably the most subtle issue. Okay, so here's some of the basic concepts in the MPI terminology. You can have processes that are collected into groups, and you're going to send a message then into a context, which is going to be, and it has to be received in the same context. So a group and a context together form one of these things called a communicator. The example that I mentioned already is the com world, which is the communicator. The MPI com world is the communicator of the whole world. And then you've got this idea of a rank that I've talked about before. Okay, so there's also an idea of MPI Datatypes, because really what's happening in MPI, it's a very low-level programming model, and what you're doing is you're taking the bytes that are sitting in memory, you're going to pack them into, the implementation is going to pack them into a contiguous chunk of data and send it off across the network in the system, and you're going to have to take it apart on the other side. So you have to be very careful when you write MPI programs, because you can put in one thing and try to take it out as something else, because it no longer has its type information as it goes through the network. But you do have data types that tell you what you're putting into the message to make things a little bit easier. So there's the int, for example, and double are two of the common types. There's also contiguous arrays, which is going to be the most common thing probably that you'll want to send. There are much more sophisticated data types in MPI, so that you can have indexed blocks of data and things like that you want to have. So if you have a bunch of different blocks and you want to send them all with one message, you can ask MPI to do that for you by using one of these more complicated data types. It tends to be a part of the MPI implementation that's not very well optimized, and as a result, people don't use it, and as a result, people don't optimize it very well. So there's sort of this unfortunate cyclic trade-off here that in practice, what people tend to send are contiguous blocks of data, and that's what's well optimized across MPI implementations. So there's also something called tags, and tags can be used to keep track of which messages, to make sure that you don't have a receive that's lining up with the wrong send message. Okay, so let's just talk about basic MPI. This is called a blocking send. And so you want to do an MPI send. Here's an array that you're going to send. You're saying the type is a double, and then the size of data that you're going to send it to. And there's the receive operation, which is going to receive it into a different array, which has a larger size, and is the same data type, that is a double. So when we do the, so that just is telling you kind of in a little bit more detail all of the things that you're sending there. And and then the last thing here, the 1 and the 0 are saying which processor I'm sending to and which one I'm receiving from. So there's no, so these are going to line up. The send and receives, this particular send and receive should line up together. So the simplest thing in a blocking send and receive is that when the function returns from the send operation, so there's lots of questions about what do we know has happened at that point. Do we know that that the receivers actually receive the buffer? And the answer is when the function send returns, what we know is that we can reuse that buffer, that A array, for something else and not worry that we're going to corrupt the message that's still going to be sent. Or we can be sure that it's either somehow been copied someplace, either into a temporary buffer or out into the network or even all the way to the other side. But we don't necessarily know that they've been received by the target process. And the and then the receive operation is going to wait for the operation, for the send to come in, the matching send to come in before it returns. So here's a really simple MPI program, which I won't read through, but you can just see the actual syntax of the MPI send and the MPI receive then, where you've got these buffers. So here you're filling in a little bit of data, and then you're going to do a send and receive from process 0 to process 1 in order to send the data. Now, MPI also has, for convenience, a number of collective operations. So collective operations are actually very popular in HPC programming, and they came from an idea of data parallel programming. So in data parallel programming, you're doing array operations. You're saying, for example, compute the sum of this array for me. Well, in a message passing model, we don't really have a notion of a distributed array. We have arrays that are chopped up into pieces. And so what you can do is you can do an operation where you get all the processors together that own a piece of that array and have them combine to compute the sum. And that's called a reduce operation. So where you're taking a bunch of data and you're reducing it into a single value. So reduces can be done with a number of different operators, min and max, product. These are typically associative operators so that it can actually reorder exactly the way those maxes and pluses and so on, whichever one you're doing, are happening within the network. There's a broadcast, which is kind of the opposite of reduce, where you're sending data out from one processor to all the others. And it turns out that this can give you a big difference in MPI application style. So any application that you write with these collectives can certainly be written with send and receive, because you can build these collective operations out of send and receive if you want to. I don't recommend you do that because on many of the systems, the MPI implementation of the collectives is highly optimized. So this is a place where there is a lot of implementation work in the MPI library, because people do use these collectives, especially the more popular ones like broadcast and reduce tend to get optimized very well. There's also an all-to-all that often is optimized very well. And so the people that build the machines and the networks and then write the MPI implementation, they may pick up a standard open source implementation of MPI, but then they will tune it to make some of these things go faster. And so usually they can do a better job. Not always, but usually the collectives will be faster than you writing your own in send and receive. Now, it also turns out that most applications that you write with send and receive can also be written with collectives. Not all of them, but anything that you write with this kind of what we call a bulk synchronous style, where you're doing some communication, and then you have some computation, and then some communication, can typically be written with collectives or with send and receive. So here's just a simple example of a computing pi. So computing pi is one of our favorite things to do in our in introductory examples, just because it's simple and you can generate a lot of work doing a bad algorithm to compute pi. But it makes it just easy to illustrate what you're doing in the parallel case. So here's an example of the broadcast operation that is sending this data from processor 0 out to the other processors. And there's the reduce operation. So there's the opposite, also an operation being done across the entire communication world. Okay, so just to give you an idea, in addition to broadcast and reduce, there are also things like all-to-all operations that will take a bit of data from every processor and send it to a different processor. There's scatter-gather operations that will go and grab data from a bunch of different processors and combine them together, or redistribute them, and all of these different things. So in the word all that happens in the front means that the results are going to be delivered to all of the processes, whereas if you use one of the non-all versions, it'll only go to one of the processors. And the V versions that have a V at the end here, that says that they're going to use a chunk of data that could have different sizes. So you're going to specify a vector of different sizes that can be used. So you could have a discontiguous set of data that will be sent with those operations. Okay, so now we have to understand a little bit about the implementation, or at least it's a little bit easier to understand what are some of the semantic issues you could run into in MPI if you also understand a little bit about the implementation. So, message passing is actually a pretty simple concept. The MPI interface standard actually came from the fact that in the late 80s, when people were kind of starting to use these clusters, there were a whole bunch of message passing libraries around. The chemistry community had their own message passing library. The physics community had their own. There were different message passing libraries from each vendor. So it was a lot of work to port an application from one to the other, just because they all spelled send and receive a little bit differently. And so it wasn't necessarily hard, although there were also subtle differences in the semantics that became very difficult. So people got together and defined this common interface, and today it's really pretty much ubiquitous in terms of the way message passing is done. But you do need to understand a little bit about where the semantic subtleties come from, and they basically come from buffering, deadlock problems. So deadlock is where you've got the processors cannot make any progress because they're both waiting for the other processor. There are places where you can get non-deterministic execution, so you can run a program twice and have it get different answers because you have written in such a way that it's dependent on the actual order in which the messages are received. And of course, the performance can vary a lot. So a question that comes up then is, when you say send, where does the data go? Well, it could just be copied into a local buffer. It could be copied all the way out into the network. It could be copied all the way out to a remote buffer, or it could be copied all the way out to the user's data structure, that is, like from the A array into the B array, and there's all these intermediate copies where it could go. So in general, you don't like to have all these copies because it wastes time making copies into local buffers. But the nice thing is that if you've copied it someplace, that the data that you don't have to worry about reusing that data that you've just sent, because the buffer that you've just sent, because somebody's made a copy of it and you can now reuse it for something else. So you want to generally avoid these kind of buffers and just go straight from the network into the user's data structure on the other side. There is one copy you can't avoid in MPI, which is the one from the user's data space to the other user's data space, and of course it does have to go through the network. But the problem with this kind of very simplistic way of sending things is if you do this, then the program has to sort of wait for the data to get delivered to the other side if you want to make sure that you get the same semantics that you had before, namely that when you return from the send operation, you can go and stomp over the data that you just sent, because in this case you want to make sure that if you stomp on it, that it doesn't actually change the result of what you had sent earlier. So this is a good thing to do for performance, but can make the semantics a little bit confusing. And you could also have problems where, if you're going to use that kind of a synchronous send and receive model, where the sender is going to wait for the receiver to actually receive the data, and similarly the receiver is going to wait for the send operation, then you can have problems with programs that don't actually terminate. So they'll hang. And so this is an example of a deadlock, which happens in this particular case because process 0 is sending to process 1 and then receiving from process 1, and process 1 is doing the same thing but in the same order. So I've left out all of the details of the messages, the rest of the message syntax in MPI, but just to see the example. So what happens is this send has to wait for that receive, and this send has to wait for that receive, and neither of them will ever complete. And so if you're using this kind of zero-copy synchronous model, then you can have problems with your MPI application deadlocking. And this does happen in real MPI applications, so it is something to be aware of. Now, it turns out that MPI will allocate temporary buffer space for you. And so you can have, so this is considered an unsafe program because it depends on the amount of buffer space that's been allocated, depending on exactly how much data you're sending or how many messages you're sending before you start to receive them. This program may or may not work depending on the amount of buffer size. And there are defaults in terms of the amount of buffer space that MPI has in the implementation, and you can change them when you run your application, but you do have to be aware of the fact that if you've written a program like this, you may have to go and fiddle with your buffer sizes in order to make sure your application doesn't deadlock. And on the other hand, when you do that, you may be using up a lot of memory on the system. So that's one of the problems that the MPI designers have with these buffers, is figuring out how much of the memory on each node do you actually want to reserve for buffers, which doesn't make it available to the user's application. So, from the user's perspective, you can avoid this by just reordering the operations more carefully. So you say, so the second size says receive before it says send, and to make sure that they're completely lined up. But of course, as you send more and more messages, trying to make sure you got all of them ordered correctly can be a little bit more complicated. You can also have use the same buffer as send and receive and do the send and receive simultaneously. So this is also kind of a way in which you can avoid the problem. Down in the implementation, now somebody has to still make sure that the deadlock problem is solved, but it's not really your problem at the interface level. You can supply your own buffer space, so you can use what's called a buffered send and a buffered receive, and so that it's going to copy your A array and your B array into and out of some temporary buffers that you've also passed in to make sure that the implementation has enough memory space for those buffers, or you can use non-blocking operations. And this, by the way, is by far the most popular way to write these MPI applications, is to use what are called iSend and iReceive, at least for the more sophisticated ones, that when you're trying to optimize for when you don't want to completely line things up. And so part of the reason is going back to this idea that the processors may not run at the same speed, even if you don't have a problem with deadlock. You don't really want your receives to be waiting for your sends and vice versa. So in fact, what you'll often do is post the receive operations as early as possible in the program, which actually allocates that data structure, the user's data structure, to write into, and then when the sends happen later, they can immediately go into the receive data structure without necessarily doing any extra copies. So the non-blocking operations return immediately, and then the question is, well, now if they return right away and they haven't made a copy of my data into the network or into some kind of a temporary buffer, how do I know when I can reuse that buffer space, that array, that user data structure? Because when it returns, it may not have copied it out of there into the network. And so when you do this, you end up having to have these handles that you then test to figure out whether or not the data structures have been whether the messages have gone out, and therefore it's safe to reuse the buffers. So you have to wait on each one of these separately when you do this, when you're doing in this kind of a model. So one thing to be aware of after you've written your first MPI application and you're trying to worry about the performance, a very common behavior is the MPI wait will seem really, really slow. Okay, if you put timers around things, it's a place that you want to always check to see what are things doing, and MPI wait may be really slow. Well, that can be for a couple of different reasons. It could be because your network is really slow on your computer, but it also could be because things are not load balanced. That is, you've said wait, but the other processor hasn't received things or whatever. So there's a bunch of kind of performance problems that can be hidden inside of slow wait operations or slow synchronization operations. You can also test without waiting. So if there's some work that you can do in your application that doesn't depend on the message being completed, but you'd rather do the stuff that you would do if it had been completed, you can do a test like this. There is a way to wait for everything, and also various kind of other variations on the waiting operations. And so then you get these different synchronous and buffered sending modes, as well as the ready mode, which is kind of living dangerously. It says, I promise that the matching receive has already been posted before I do the rsend. And so that's something that you only want to use once where you're pretty sure of how your application is being scheduled. For example, there's some synchronization, so you know it's actually complete. Okay, so perhaps the single most important thing that I've left out so far is that you can synchronize these programs. You can actually wait for them to be you can wait for all of the processors to catch up to the same point. As I said, you should think of it as if the main function is just being copied on each one of the processors, but they can go down completely different branches. So they may branch on something like the processor rank, and then they'll go down different parts of the code. And so in order to kind of get them all lined up again at some point in the program, you can put in one of these barriers. And so all the processes will wait until they get to the barrier point using in any of these different versions of the language. Okay, so let's see. One other thing I think I didn't mention in terms of kind of a subtlety with MPI, I did mention the fact that there are race conditions possible in these programs. And race conditions come when you start using these kinds of I-sends and I-receives. If you start writing into the buffer before you've determined that the buffer has actually been copied out into the network someplace, then you may or may not end up with a program behavior that causes problems, because what happens when you write on that buffer and whether or not it depends on whether or not the message has been copied yet, and you don't really know that from the MPI application level. A lot of times you won't see a race condition as something that happens on the same machine when you run over and over again at the same size, but as you change the size of the run, or you change from one machine to another, the timing will be different enough that you'll start to see those kinds of problems. So if you start to see kind of anomalous behavior like that, the first thing you want to do is go look through your code to make sure that you haven't, that you're being really careful not to have any of these places where you're reading or writing data that may not have been completely written in or completely copied out. Okay. So, the good and the bad about this whole ecosystem around MPI is it allowed an enormous number of applications. So we have about 700 different applications that run today on the NERSC systems that you're using. Some of them are standard commercial off-the-shelf software like VASP. Others are custom built by each one of the graduate students who logs into the system. They write their own applications. I'm hoping that's why many of you are here. So the nice thing is that it's been a de facto standard for writing these kinds of large-scale, high-performance computing parallel applications. The disadvantage and the advantage of that, is it allowed all of these things to allow people to write applications that were actually portable across machines, not just machines of the same generation, but machines of many generations. So for many years, you've been able to take an MPI application and move it from one platform to a future generation system, the next generation system. And you may have to do some work on performance optimizations with each new system, but generally those applications will run with only a modest amount of kind of configuration work. On the other hand, it's kind of frozen things in terms of how we program in parallel in this mid-90s sort of architectural technology. So it doesn't really match GPUs very well. It doesn't match multi-core or many-core processors very well, and it doesn't even really match these big hybrid machines now like Hopper that has the 24-core shared memory nodes. So the programming model, for better or worse, these programming models have reflected the hardware. When we had these vector computers, we had vectorizing compilers, and now we have more of this, now we have these message passing things. And now everybody is starting to put things like OpenMP into their MPI applications to deal with shared memory, except that if you think the future is with GPUs, you put in CUDA instead of OpenMP, or maybe OpenCL if you want to bet on that. So there's a lot of different things that people are trying to do. So there's not a clear kind of next direction for everyone to take in their applications. So Horst Simon, who's the deputy lab director actually at Lawrence Berkeley Lab, and used to be the head of computing sciences, but I worked with him there, said, I'm not sure how it will program a petaflop computer, but I'm sure it will need MPI. He has now said the same thing. I forget what the date is, but about an exaflop computer. Basically, MPI is not going to go away in the exascale arena, but we do expect that something very different is going to happen within the nodes, because even on Hopper, using an MPI process per Hopper core is typically not the right thing to do, and I'll say a little bit more about that. Okay, so here's some references to MPI. If you want to look them up later, there's a bunch of books on MPI. So there's actually a fair amount of both online and printed educational material for learning about MPI. But you have sort of hopefully the basics of it. You could write your Pi program at the very least and modify that to do something a little bit less trivial if you wanted to go in terms of starting your homework assignment. Okay. So I'm going to spend the rest of the time talking. Let me just see if there are any questions about MPI. Yes?
One of the things when I started reading about MPI that charmed me very much was that there was a notion of the topology of the interconnect network being incorporated into the language so that the system knew what the topology was. Until I was very enamored of that, until I saw that only works for a mesh architecture and not for a really interesting architecture like stars, non-uniform memory.
Right.
Why is this?
So the question for those of you who are not here or couldn't hear it is about the fact that in MPI you can actually get information about the topology and program to the topology, but the topology is very limited. The operations are very limited in the fact that MPI really looks like some kind of a mesh underneath. So the problem is there are all these other networks. Most of the machines today, the most popular network on most of these systems is some variation of a torus network on the large systems. The smaller clusters will have other kinds of networks, and a lot of times they're not a pure torus, so it's like a mesh, that wraps around a pure torus all the way to the bottom. But I think the reason that it uses a mesh inside of MPI is because many physical applications do have a natural kind of locality decomposition of the data that you're simulating over. If you've got a physical domain that you're simulating, then you're going to chop that domain into pieces. And so there's a very natural way of thinking about the nearest neighbors of the different physical parts of the domain relative to the other processes in the implementation. And that can be useful then in mapping onto a lot of the networks. The problem is then if you try to put a lot of other topologies in there, it can get very complicated. But that's I think that's really the reason it has to do with it's sort of a common programming model, and it also tends to help somewhat in the mapping. And what we find in the networks in terms of the performance and how important topology is, for many years topology was not very important. And if you're programming on one of these smaller clusters, you probably do not need to worry about the topology of your MPI application, exactly where each process sits. If you're programming a very large machine on, say, a torus network, and actually there's kind of a split right now between blue gene machines where you can optimize for the torus interconnect there, and the Cray XE machines like Hopper, where the job placement is not such that you can really get much control over physically where the layout is. So I think it's because it's sort of useful in some of the applications, and it can be helpful on some machines. But it gets very complicated if you try to put in a more general set of topology primitives. Any other questions about MPI?
Yes.
Yes.
How do you with the MPI know that there are 100 or 1,000 machines in my distributed system? Can you install it? Is it a config file, or how do you?
Okay, so this is an MPI installation question. So some of the TAs in the back may want to help out But yes, when you install it, when we install it at NERSC, so we install it for you on the NERSC systems, and when it gets installed, it says how many physical processors there are in the system. But it's really, when you run a job, you have this little job script that says, I want to run a certain number of processors right now. That's what determines then the MPI in your MPI program, how many processes it has available to it. Any other questions? By the way, there's lots of performance tuning also that goes on depending on the size of those MPI, those machines, because of the topology issues, for example. Okay. Any other questions? Okay. So partition global address-based languages are kind of have been a competitor to MPI for a while. They haven't really taken over message passing at all, but they do have some interesting ideas, and people are actually more interested in them today than they've been for a long time, mainly because they give you kind of the ability to do shared memory and message passing in the same programming model. So the other way to think about these, the other phrase that will come up is one-sided communication, and I'll tell you what one-sided communication is. So what's wrong with the idea of running an MPI application on every core? Well, as I said, it works pretty well on a small number of cores per node, that is on the Franklin system. Hopper, it's not such a big problem in terms of performance for many applications. The big issue is the memory footprint. The MPI implementation itself consumes memory for each process. The user's application consumes memory because MPI forces you to chop your data structures up. And if you have a data structure that you really need to have shared, that is, everybody needs a copy of it, then you're going to make a replica of that in each one of your processes, and that consumes memory. Even your ghost regions, so your halo regions or whatever you call them around a particular domain in domain decomposition are going to take up memory. So just a little little calculation here. If you've got thousands of processor cores on your system, or let's say you've got 100 cores in each one of your nodes, and you're running little tiny 10 by 10 by 10 blocks on each one of those cores, each of which has to communicate with its nearest neighbors, half of your mesh points are on the surface. So you're going to be replicating half of your mesh points across the other processors. So this is a real issue in, maybe not because you're not necessarily running such a small one of these grids, but the amount of replication that happens in an MPI implementation, the memory footprint, is a big issue. And so we see that at NERSC, people really are switching to a hybrid programming model with OpenMP or something like that, or pthreads, POSIX threads, inside of the node in order to avoid the memory footprint problem. So these PCAS languages, though, give you the ability to write both a large-scale distributed memory application and one that works well on shared memory, all in the same language. Now, I'm going to talk mostly about UPC, and I won't give you a real detailed overview to it, just try to give you sort of a sense of what UPC is like and how it's a little bit different than MPI. I should point out that there are a couple of free implementations available. Both of them you can get to from the LBL webpage from upc.lbl.gov. It runs, for example, on Mac OS. It runs at least at times on, there's versions of it that run on Cygwin on top of a Windows machine if you want to. It runs on most of the supercomputers available today, including the systems at NERSC, and we're always working on having implementations that run on the future systems. There are commercial compilers for both UPC and co-array Fortran from Cray. IBM has a UPC one as well. HP has had a UPC one for many years, and so there are a couple of commercial ones. For UPC, there's also a GCC-based implementation, a GNU compiler, which uses actually the Berkeley runtime from our compiler, but is the GNU compiler, and that's from a small company called Intrepid. So one of the first things I learned, because I'm a language researcher, is if you want people to actually use your language, you have to give them a lot of security that the language isn't going to disappear. And one of the ways of doing that is to make sure there are multiple implementations. They have to run everywhere, and you have to be able to prove that you can port them from one machine to the next without too much effort. It is a fair amount of effort to port MPI from one machine to the next. It's not a unsurmountable amount. Every vendor, when they design a new network, has to put a team of people to do the MPI port on that. But and the same thing happens with the network infrastructure underneath UPC. But we basically demonstrated that you can get something that's portable, and there are free implementations of it around. You may get better performance out of the more expensive compilers, just as you would with a comparison between GNU Fortran, for example, and a commercial Fortran compiler. So the philosophy in UPC is based partly influenced by C, that you're trying to get good performance. And there are things you can do in C that can get you into all kinds of trouble. We're not going to try to stop you from getting into trouble in the UPC implementation. We're going to basically give you kind of an abstract machine model of the system, but hopefully make it more convenient to program, especially for some of these large distributed irregular data structures, than it is to program an MPI. An MPI, you're going to have to pack, when you have these irregular data structures, you have to pack up pieces of them and send them to the other processors, and then unpack them on the other side. It was based also on some previous languages, including Split C, which was a language done here at Berkeley by David Culler and myself. We're involved with that, along with a number of students, and some languages from other places as well. Okay, so the UPC execution model, the parallelism model, is really the same as MPI. We call it a SPMD, SPMD, single program multiple data model. Now, Rusty Lusk, who's one of the people who has spent many years in the design of MPI, will object to this, because in MPI you can actually write non-SPMD programs. You can have different parts of the MPI application go off and do different things. But most MPI applications and all UPC applications are written in this single program multiple data style, which is what I told you was the intuition behind MPI. That is, you take a copy of the main function, you just replicate it, and they all run the same thing. And the reason, by the way, MPI allows you to do more general things is you could have, for example, an ocean model and an atmospheric model and a sea ice or a land ice model, and these different parts of something like a climate model that can all be have been written separately as separate programs and be merged together. But in this SPMD model, there's a fixed number of threads that are started when you start the execution. They run all the way to the end of the execution. You can ask for my thread. So now in UPC, because there's shared memory, we tend to use because there's a global address space, so you can read and write data anywhere. We tend to use the word thread, but it's really the same as an MPI process, except that they can see the other processes' data. There's a barrier for synchronization, just like an MPI barrier. There's also kind of a version of a parallel loop that I'll talk about a little bit later. You do have to worry about this threads variable. Is one that you're going to get slightly different kinds of programs depending on whether you compile it in what's called a static thread mode, where when you compile the application, you tell it how many threads you want to run with, versus a dynamic thread mode. And what comes up there is, for example, is it a compile time constant that can be used in array, in the size of an array, and declaring an array. So here's our simple hello world program in UPC. A little bit easier than the MPI implementation of it. There's just this, but we've got the same sort of C program here, but there's no initialization because it's a language. The compiler has done the setup for you. You do include this UPC include file in order to get access to some of the standard variables like my threads and threads. Here's our slightly different variation of computing pi calculation. We're going to throw a bunch of random darts at x, y coordinates and then figure out what percentage of them fall into the curve. So this is all mostly just C code here. So this is just the serial implementation of it. You can actually, any serial C program is also a UPC program, so you can take this and run it, and what you'll get is all the processors computing the same value, the same approximation to pi. So not particularly interesting, but it does compile and run. So each processor is going to get its own copy of each of these variables inside of a UPC implementation. By the way, you have to be a little bit careful when you call any kind of a built-in library. You need to know whether the library is reentrant, that is, whether you can have multiple threads inside of that library. And so because UPC is going to run on an underlying thread layer when you're running on shared memory hardware, that is something that you have to be aware of. So this is, as I said, completely independent calculations of pi. Now we can make it, and here's the code that's inside of those functions. It's just some serial C code to square the numbers and so on. But now to make it more interesting, we have to use the global address space. So what does the global address space look like? First of all, there's two kinds of variable. There are the kinds that we had in the previous example, which are regular C variables. Those are called local variables. And then there are things called shared variables, like the shared variable hours. And here's the cartoon of what the address space looks like. The deal in a partition global address space language is that any process, any one of these threads, can read or write the data that's up in this shared space. And so in particular, if you just declare a scalar variable like hours as a shared variable, every thread can access that and it'll get the same value. Okay? So that's a pretty bad thing to do if you're going to run on a 100,000 processor application. All of them read and write this hours variable. It's going to be very expensive. So we tend to not use those a lot in UPC applications, except as things like constants that are going to end up, that the compiler will be smart enough to replicate for you. But this idea of shared then just gives you the intuition that you need to do something more interesting. We can write the pi example using the shared variable. So here it is using a shared variable called hits, and you're doing the accumulation where you're accumulating the number of these trials that are hitting inside of the unit circle or quadrant in this shared variable. Now this has a problem from shared memory programming. What's the problem? Yeah, you got a raise condition in this program because all the processors can actually be writing to this variable hits, which is all the same variables. They're not separate variables at that point. We could solve it by a number of different ways. UPC has locks, which I don't think I'll have time to tell you about, but you can lock on that variable. That would give you a correct program, but a very slow program. You can also write something that uses arrays so that everybody has their own temporary copy that they're going to do their hits into, and then at some point do an accumulation in order to get to a single final value out of that. So shared arrays in UPC are going to be spread out over all the processors. So this just shows you a picture of which element in each of these array declarations thread 0 will own, and they just wrap around. So if you've gotten through all the threads, then they'll wrap back around to the beginning. In multidimensional arrays in C, you really should just think of them as being flat linearized chunks of memory because that's what they are, and so those elements will also wrap around. There are ways in UPC to also declare these arrays as blocked in various ways, so you get a whole chunk of a certain size of, say, red things that all live on processor 0, so you can put a block size into the declaration. So here's the pi example done now with one of these shared arrays. So instead of a scalar variable, all hits is a shared array, and they're all actually doing these accumulations into their own threads element of that shared array. So that's a variable that's going to live locally inside of that shared array. And then at the end, just one of the threads after this barrier, one of the threads is going to run around, read all the other values that are in the array, and add them up. Now, there are faster ways of doing this because this is a sequential algorithm that's going to run through the processors and read all of those remote values from the other processors' memory spaces. And you can do this with collective operations as well in UPC. So UPC has very similar collectives to MPI. But that just gives you sort of the idea of what the address space looks like. There are more sophisticated barrier operations as well as the locks that I mentioned before, but I won't go through the syntax here. So just to sort of see the collectives, this is the collective. So there's the all and the V are common naming conventions between MPI and UPC, And so this is just using a reduction operation to collect all of the results together after people have done local computations into a local variable myHits, and they all contribute myHits into a reduction operation that is being done as a what we call a value-based collective. So we call these collectives because, once again, as in MPI, you're getting all of the processes or all of the threads together to perform some kind of global computation, either to communicate data in something like a broadcast or to communicate and compute on data as you're doing in a reduction. So there is a UPC for all, but I think I will skip going through more of these details. There are, there's some examples here if you want to look in a little bit more into UPC in terms of exactly how you write this kind of a program. But you can do things like have these shared arrays, and then the parallel for all statement is what you can use to distribute work across the different processes. It's kind of in between an OpenMP parallel loop and an MPI, which forces you to chop up the iteration space completely. This allows you to write one loop construct, and there's this extra argument in there that says if I'm the thread that owns that owns that value I, well, in which I mod the thread number is equal to my processor ID, then I'll actually execute that iteration of a loop. So it just makes it a little bit easier to distribute loops in parallel. And I mentioned there were some blocking factors. So what do I mean by one-sided communication and some blocking factors in the arrays? So just a little bit about one-sided communication, how it's different than two-sided. And I bring this up because it is a topic of debate. MPI 2 put in one-sided communication. It was generally not considered a very useful interface. We actually have a paper on what's wrong with the MPI one-sided implementation relative to our perspective as language implementers. But the MPI community who are writing applications also felt that it wasn't really what they wanted. The vendors had some trouble implementing it as well. But there's been enough evidence, and I'll show you some of that, for the value of one-sided communication that people are still very interested in it. And some networks do a very good job, like the Gemini network on the Hopper system actually has very good support for one-sided communication. So what do I mean by one-sided communication? Obviously, there's two sides in any kind of a communication, so what do I mean by one-sided? The difference is that in one-sided message, like a put operation, instead of sending a message ID, you're sending an address along with the data. Whereas in an MPI message, you send a message ID. So why is that significant? It's significant because when a one-sided put operation gets across the network to the other side, it gets picked up by the network interface hardware, and it can be directly written into the memory on the other side without getting any information from the host processor on the other side, without doing any kind of synchronization or anything like that. Whereas a two-sided message, even if you've pre-posted your receives, somehow the network interface or whatever's going to write that into memory, and normally it's going to be the host CPU, has to get some information about what address did the receive operation have in it. So it doesn't know in this message, there's no information about where it goes in memory. And what you do in UPC is you set up your data structures ahead of time so you know as a programmer where all the remote data structures live so you can directly write into them. So it has some performance advantages. This is the bandwidth of MPI versus GASNet, which is the communication layer underneath our UPC implementations and the GNU implementation. So you got higher bandwidth across a bunch of different systems. You get lower latency from GASNet, so faster small message performance, about the same large message performance, which is what you would expect. And when you have medium-sized messages, you also see an advantage. So the real advantage in GASNet is that this is higher bandwidth that you get for these 4 kilobyte messages, is that there's less bookkeeping because there's less there's no synchronization at all or bookkeeping associated with GASNet. All you're doing in UPC when you say to write something is it's just writing the data into the remote memory. It's not notifying the other side that the data has been received. Sometimes you need that for the application, in which case you need to do it separately with some kind of a synchronization operation. So this has also been used to show that, you can get good performance out of things like 3D FFTs. So the best UPC implementation here is faster than the best MPI implementation. This is some very recent work, actually, by some others at NERSC, including a postdoc, Robert Preissel, looking at co-array Fortran. So this is not UPC, but is another PGAS language, co-array Fortran. It's showing that in this, and this is actually in a GTS, which is a gyrokinetics code for fusion simulations, that you can get better performance out of this co-array Fortran than you can out of MPI on the Hopper system. And this is a Best Paper Award nominee for Supercomputing 2011, which is coming up in November. So, beyond this sort of model, I'll just say that we are looking in both MPI and in UPC at what is beyond MPI or MPI plus OpenMP and UPC, and trying to figure out kind of what's the next big thing, and are we going to have something like some kind of a GPU 2010, I guess 2011 model. So we're no longer really building the systems out of straight COTS. We're putting there's various kinds of levels of accelerators in the hardware, either in wide SIMD units or in GPUs and things like that. So these are no longer kind of sustaining our ecosystem, so it's really time for a change. And I think the interesting thing is that the kind of programming that you do on GPUs, and I'll just kind of leave you this idea as a food for thought. When you're programming on a GPU, what you're doing is you're reading and writing one-sided communication into the GPU's memory, and then kind of triggering the GPU to go off and do some computation for you. So that one-sided communication model is actually quite consistent with these PGAS models. And what you have within the node of a GPU system is a partitioned address space between the CPU's memory and the GPU's memory. So we are working on adapting UPC. We have some initial versions of it running to run on top of clusters of GPUs. And with that, I will stop and see if there are any questions about GPUs, UPC, or any of the, or MPI for that matter. Yes?
In any of these applications, do you ever see any memory leaks or any kinds of... Oh, sorry.
Thanks.
Do you ever see any kind of memory leaks?
Memory leaks in the application or in the runtime system?
Either one.
Either one. So, if there's a bug in the MPI implementation, there are times when we see MPI implementations that do have memory leaks in them. In UPC, it's entirely up to the user programmer, the application programmer, to manage their own memory. Actually, in MPI as well. So yes, you can certainly write applications very easily that have memory leaks in them if you're not careful about managing and reclaiming your memory afterwards. But we would consider that a bug in either the UPC implementation or the MPI implementation if the runtime systems had memory leaks in them. We have, over the years, that's been an error that we have found from time to time in various implementations, is there's some kind of a memory leak. And there's various things that can leak besides just memory. There's like these registration IDs and things like that with a network interface. So there's basically resource management problems in the runtime system. You can run out of a bunch of different things in the implementations. But we try to avoid that.
I was wondering, with these large systems, how you deal with reliability, like just hardware failures. Is there any kind of recovery on some of these different languages?
Yeah, so that's a very good question. It's one that people are talking about a lot as we move to exascale, the question of reliability of the system. So just to give you a sense, the network in the Franklin system, which actually has more cabinets than Hopper, because it's only quad-core, it's got 100 cabinets versus Hopper, which is a 68 cabinet system. The network on that system, so the processors are fairly reliable. The system is resilient to individual node failures. So a processor can fail, and the system will keep running on both of the systems. The difference is that on the older network, on the Franklin system, if the network fails, the whole system goes down. So that's a big problem for us as somebody that runs one of these centers. And so Hopper's actually been much more reliable from that standpoint, because you can actually pull a network link out and the system will keep running. That said, if you're running a large job across the system, or you're running it for many, many hours, you can see a transient error. And we are seeing in these very large systems, especially depending on where they are, if they're up in the mountains and things like that, you'll see a higher rate of transient memory errors and things like that. So it is a big concern trying to detect these errors. People said, though, we would never get a petascale machine to run, and we do get petascale machines to run, and they get a lot of useful work done with them. So I think we have to be a little careful in exascale not to overdo this. We assume in the Nurse Center that people have checkpointing code in their applications, and so there are some tools to make that a little bit easier for people. Other questions?
So there's also some questions from the internet. Does MPI give any sort of performance guarantee? And another question is, how does processor-to-node mapping affect collective communications?
Okay, so the first question about does MPI give performance guarantees? I would say it does not give any particular performance guarantees in MPI in terms of like real-time guarantees or anything like that. There's nothing in the specification or anything that will give you a real-time performance guarantee. On certain systems, you can obviously measure things, and you may have more predictability on one system than another. Some systems are much more susceptible, for example, to cross-traffic in the network than others are. There's kind of a trade-off there when you're running these big machines of whether you force a job to be completely contiguous in one of these torus networks or not. You'll get more dependable performance if you force them to be contiguous, but you have all these little cracks then that you don't get to use, so you have lower utilization of your system. So we tend to pack our jobs pretty tightly at NERSC. And let's see, the second one was about the mapping of processes to actual physical nodes in the system and how that affects performance in the collectives. And I would say that is a big factor in collective performance. And in fact, there's a couple of students around who've been looking at that particular issue on the Blue Gene P system and kind of trying to get a handle on it on the Hopper system. But right now in the Hopper system, it's a little bit harder to control exactly that layout, but you do see some big differences in collective performance. Good questions. Anything else? Okay. Thanks very much.